This is the fourth topic. We're going to talk about Gauss' law. And we're going to use Gauss' law to find the electric flux density and the electric field for simple charge distributions. And this is the learning outcomes. So at the end of this topic, what I expect you to know is to be able to find the electric flux density and then using that to find the electric field. Okay, so earlier on in the previous topics, we introduced the electric flux density so that we can find electric field easily in dielectric materials, because the electric flux density only depends on free charge, whereas the electric field inside a dielectric materials depend on free charge and polarized charge as well, or depolarizing electric field inside the dielectric materials. So here we're going to use Gauss' law to find electric flux density. So at the end of this topic, you should know how to find electric flux density D using Gauss' law, and then use that to find the electric field. And then also expects you to be able to draw lines of electric flux density and electric field for simple charge distribution. So that is what you are expected to know at the end of this particular topics. So recap what we have talked about on electric flux density D. We define a new vector field which is called the electric flux density D. So we did that in the last lecture on topic 3. And then we also introduced the relationship between the electric flux density and the electric field. So the electric flux density is equals to epsilon r epsilon naught times the electric field. And we said that the epsilon r is the relative permittivity, or sometimes called the dielectric constants of dielectric materials. And this dimensional number quantifies the strength of the polarization. So different materials, it polarizes differently, and therefore it has a different epsilon r value. And that is what we have talked about in the last lecture on topic 3. And D is just E scaled by a factor of epsilon r epsilon naught as shown in equation 1. So D is equals to epsilon r epsilon naught times the electric field. So for linear and isotropic materials, that is what we're going to use or talk about in this module. So epsilon r is just a scalar value. It's not a vector or a tensor. It's not three-dimensional. So it is the same every direction of the materials. Okay, so if I have a materials, so doesn't matter where the electric field is, epsilon r is the same. The polarization is the same. It doesn't matter where I apply the electric field. This is what is known as linear and isotropic. So if I apply my electric field in these directions, the polarizations of the dielectric materials is the same as if I apply my electric field in this direction or in this direction. So in 3 different dimensions of my materials, how I apply my electric field, the dielectric materials polarize the same way. And therefore, this value here, epsilon r, is just a scalar value. There are some materials which is called anisotropics. If you apply the electric field in these directions, you polarize differently compared to if you apply the electric field in these directions. In those sort of materials, then epsilon r is not the same in all three dimensions. It's different in different dimensions, and therefore this value here is not a scalar. It is a 3 by 3 matrix. And in that case, it is an anisotropic materials and it's not linear. But this is not what we're going to study in this module. We're just going to treat epsilon r as a scalar. So it just scale the d by a factor of epsilon r epsilon naught. And for all cases, epsilon r is greater than 1. So all dielectric materials compared to air, you have epsilon r equals to 1, and the equality, meaning epsilon r is equals to 1, is where we have free space, i.e. a perfect vacuum. But we normally treat air, atmosphere, as 1 as well, because it's quite close to a perfect vacuum scenario. So in the atmosphere like this, epsilon r, we treat it as 1. But it's not actually exactly 1, but it's good enough for us to treat it as 1 as well. But to be absolutely 1, we are talking about perfect vacuum. Okay? But in all our problems that we're solving, as long as we talk about air, we treat epsilon r as 1. Electric field inside a dielectric is produced by both free and polarization charges, whereas the electric flux density is produced by free charges. Okay, we have looked at this when the dielectric materials is polarized, and then the electric field inside the dielectric materials depend on the free charge, which is the applied electric field that we talked about previously. So we said that we have a dielectric materials put in the presence of EA, applied electric field. This applied electric field will give or will cause the dielectric materials to polarize, and when they polarize, it creates a polarization P, and because of that, it creates a depolarization field, and then that gives us the actual electric field inside our dielectric materials. Okay, so what it means is that this dielectric materials electric field depends on both the free charge from the applied electric field and also depend on the depolarizing electric field. Okay, we look at that last lecture, that E is equals to EA minus EP. Whereas the electric flux density doesn't depend on the depolarization charge. And therefore, it only depends on free charge, and therefore it makes things simpler by introducing this electric flux density. And then there's a statement here said that D cannot be directly measured using experimental equipment. So we can't measure the electric flux density. We can measure electric field quite easily, practically, and this is more practical meaning. They have more practical meanings, meaning that we can actually measure them. Whereas the electric flux density, we can't verify that experimentally. It's just a concept introduced. So within a linear isotropic dielectrics, the lines of the electric flux density look exactly the same as the electric field. They are parallel to each other at all points. Okay, the difference is that there's just a scale factor between them, epsilon r, epsilon naught. But if you look at the field lines, they look exactly the same. So we talk about electric flux density. So it only makes sense if we talk what is electric flux. So electric flux through a surface or a plane surface. So we introduce electric flux with a symbol, capital phi, with a subscript E, and we call that the electric flux. If you know what's magnetic flux, the electric flux is just the equivalence in the charge or the static charge domain. Okay, so it is similar to what you know about magnetic flux, but the equivalent of that in electrostatics. So we define the electric flux density. So density means that the number of lines per unit area. So density, how many of the electric field lines going through a particular area, and that's what density means. Okay, so the electric flux density is referring to the number of lines per unit area, and that's what the electric flux density that we introduced actually means. So to put that into perspective, so if I have an area, okay, so this is my area, my electric flux density is how many of my field lines going through this area that I have. Okay, so in this diagram here, I draw a circle in a slanted way. Okay, so meaning that this is perpendicular to the surface of my circle. So I have a circle, so I'm looking it in, so this is my circle, I'm looking at a slight direction, so I have how many lines going through this circle, and that is what we call our electric flux. So it's my D times the surface area. So D is the density, how many lines going through this area. So the electric flux will be this area times my electric flux density. Okay, so electric flux density is how many lines going through a particular surface. So the electric flux has to be the flux density times the surface area. In this case here, if I have my circle here, my field lines is going in this direction, so it's not actually going through my circle. So therefore my electric flux is 0. No flux going through the area that I define. Okay, so the first one, perpendicular to my surface area, so the electric flux equals to the electric flux density times this surface area. The next scenario that I show there, if my field line is going in an angle, okay, if I have an angle, then I can resolve this field either one component in the horizontal and one component perpendicular. Okay, so you learn about vector. So if I have a vector like that, you can resolve this into two components, one in horizontal and one in vertical. Right? You learned that, right, in maths? So this, if I have this thing here, this component, if I have data, so this component resolve to my x-axis. If I call this A, this is simply A cos theta, right? And the one into my y-axis, that will be A sine theta. And that's my two components. So in the same way, if I have my circle, I have a field that is going in an angle. So I have one component, this field cos theta, it will be perpendicular to my surface. That field sine theta, that will be horizontal, and that field doesn't cut through this surface. Okay, so that is this diagram here. So I have my field in an angle. Sine theta is the one that is perpendicular, so this gives rise to one component that is perpendicular to my surface, which is similar to this. And then at the same time, if I take sine theta, then I have a component like that. So this will be, so this is sine theta, and this is cos theta. And this component will be similar to this. Okay, so this doesn't cut through my surface, but the black one does. So my field lines going in an angle times cos theta is the one that is cutting perpendicular to the surface. Sine theta missed the surface altogether. It's going horizontally. And therefore my electric flux will be my electric flux density times the surface times cos theta. And that is the actual flux that's go through the surface of my circle that I draw there. Okay, so you get the concept? So perpendicular to the surface, the electric flux density perpendicular to the surface times the surface area, that is my electric flux. If it doesn't cut perpendicular to the surface, you resolve that to two components, the one that's perpendicular and the one horizontal. And the one perpendicular is the one that you multiply with the electric flux density that gives you the electric flux. Okay, so that is electric flux density. So to make this easier, it will be good if we can define a new vector. So if we define something called a surface vector S, so my surface, I define a vector that I call S that has the surface area times a unit vector which is normal to that surface. So this is my, okay, if you think of this as my circle, my vector S is my surface, is my area vector, and that is perpendicular to the surface area. So now my D will be an angle theta from my vector S. And therefore we can write down our electric flux as a dot product of two vectors. Dot products, we know about dot products, yeah? A dot B. That will be the magnitude of A times magnitude of B times cos theta. So just now, the previous slide, we said that the electric flux density equals to D times S times cos theta. So we know that this is a vector. So we define a new vector for the surface so that we can use a dot product for that. So if we do that, so D dot S, then it worked out nicely that only the perpendicular or the normal to the surface will be S times cos theta. This is our equations. Our electric flux is defined as D dot S, and S is a new vector we introduce that we call any surface, okay? The vector is perpendicular to that surface. So if I have this surface here, then any point of this surface will be perpendicular to this surface, any point you look at. Okay? So that is my surface or my area vector. And this vector S has a magnitude, has a unit of meter square because it's in an area. My surface my surface area vector S has a unit of meter squared, just like any area, but except that this area that we define is a vector. Although normally area is not a vector, we define it for convenience here so that we can introduce an equation for the electric flux. So d dot ds and d dot s, s is the surface area vector. And we deliberately define this vector to be normal to the surface. Okay, so our electric flux density units is coulombs per meter squared. Our vector surface is meter squared, and therefore our electric flux is coulombs. Okay, so our electric flux is equals to D dot S. We know that D is coulombs per meter squared. And just now we know that this is area, this is meter squared. So this gives us coulombs. So what has a unit of coulombs? Charge. Okay, so that tells you that this equation somehow still has to be equals to charge, right? Because it has a unit of coulombs. Our electric flux has a unit of coulombs. And we know that charge has a unit of coulombs. Go back to our area vector. Our area vector has a magnitude of S. S is the area of the surface, and it points outwardly from the surface, or perpendicular, normal to the surface. Okay, perpendicular to the surface. Okay, so this is the equation. Electric flux equals to D dot S. Dot is a dot product.